Welcome back. We are now going to look at what the second derivative means with regards to graphing functions. So I've picked a function, y equals x cubed. First derivative, I'm hoping you all know that that is 3x squared by now. And the second derivative would be 6x. I'm going to not worry about the first derivative right now. We talked about that in the previous video. But the second derivative being 6x. Well, if we graph that, that's going to be a line with a y-intercept of 0 and a slope of 6. Notice right here, that's where, I'm going to switch to my other notation, that's where f double prime is equal to 0. What does that correspond to on the graph of my original function? Well, that corresponds to a point of inflection. And all of these values, those values are where f double prime of x are greater than 0. And if we look back over here, this part of the graph happens to be concave up. That part, that has our second derivative less than 0, and going back to our original graph, that's this portion, and that is concave down. So let's summarize this. If the second derivative is less than 0, then f is concave down. If the second derivative is positive, f is concave up. And if a curve has a point of inflection, its second derivative must be 0 at that point. Now, it's not necessarily true that the converse of that statement is true. It is not necessarily true that if the second derivative is 0, there must be a point of inflection. Not always true. You can't make that assumption. You're going to have to use a sign diagram. So, let's take all of this goodness and bundle it up into one wonderful problem where we're going to analyze the graph of f of x equals 2x to the fourth minus 4x squared plus 1 without actually having a graph. Whoa, crazy, I know. We're going to find any maximums, minimums, or points of inflection. We're going to find the intervals where f of x is increasing and decreasing, and we're going to find where it's concave up and concave down, and then from that information, we are going to graph it. Whew, okay. So what do? Well, we need the derivative. Let's start there. F prime of x. This is telling us about the slopes. This is going to find us our critical values. Our derivative is 8x cubed minus 8x. Okay, so we saw this in the previous example. This was the same problem, but we'll run through it one more time. To find part A, the max, min, points of inflection, yada, yada, we need to set this first derivative equal to 0. And this is factorable. And we get critical values of 0 and plus or minus 1. And since we're actually going to be graphing this, I want to know what the function values are. I want ordered pairs. So f of 0 is 1. F of 1 is negative 1. And f of negative 1 is negative 1. So what I know right now is that 0, 1 is a point on the curve. 1, negative 1 is a point on the curve, and negative 1, negative 1 is a point on the curve. Question now is, since these are critical points, are they minimums, maximums, points of inflection? I don't know. Let's find out. So what do? Remember, we make a sign diagram. Negative 1, 0, 1. And we're going to test values in between each one of these critical values. So for instance, the derivative evaluated at negative 2, That was less than 0, which means that this is decreasing. The first derivative evaluated at, say, negative 1/2 was greater than 0, so this is increasing. First derivative evaluated at 1/2, that is less than 0, which means the function is decreasing. And the first derivative at, say, 2, a number over to the right of 1, that was greater than 0, so we're increasing. So we have a minimum at 1, negative 1, and negative 1, negative 1. And we have a maximum at 0, 1. And we also know that this curve is decreasing on the interval negative infinity to negative 1. And so we use union. It's also increasing from 0 to 1. Notice I'm using open intervals here because these places where the first derivative was equal to 0, it's neither increasing nor decreasing. And then increasing. X is an element of, what do we have here? The open interval from negative 1 to 0. Remember, you could use parentheses for this also. Union with one to infinity. Okay, cool. So what does this mean? Well, if I were to draw a quick, rough, icky, dirty sketch, I know the basic shape of this curve. Looks like that. Question becomes, what's the curvature like, and where are these points of inflection? I'm hoping that you can maybe see it sort of does one of those numbers. But if not, that's okay. We're going to continue to do some mathematics, and we're going to move into the second derivative. So this is going to be 24x squared minus 8. And if we want to know about concavity, we need to know points of inflection. We need to find out where this is equal to 0. So x squared equals 1/3. X is equal to plus or minus 1 over the square root of 3. Now I hope that you see that finding the actual points of inflection without technology here is going to be a little bit difficult because we're going to have to plug in 1 over the square root of 3 up here. We can do it. It wouldn't be horrible. I'm going to save us the time in these notes of actually calculating them. I'm going to tell you that the 2 points that we get are 1 over the square root of 3 and approximately negative 0.11. I think exactly that ends up being negative 1/9. And negative 1 over square root of 3, comma, negative 1/9 also. So these are 2 points. The question is, what kind of concavity do we have? These are both maybe going to be points of inflection, but we don't know until we draw our sign diagram for the second derivative. 1 over square root of 3, negative, positive 1 over square root of 3. Those are the 2 critical values I get from the second derivative. Now we need to test to see, is the second derivative positive or negative? So we test in between the two, f double prime of 0. that is going to be negative. So that means that F is concave down. And of course, on a formal assessment or anything else that you're doing, you should write concave down, not CC, arrow pointing down. Then we check something to the right, say F double prime of 2. I guess we could even check 1. 1's greater than 1 over root 3. And if we do that, we get that that is positive. So F is concave up. And checking a value to the left of this critical value, we get that this is positive. So F again is concave up. So since we're changing concavity at these 2 points, at these 2 critical values, we know that both of these are points of inflection. And the intervals that were concave up are when x is an element of negative infinity to negative 1 over square root 3, also 1 over square root 3 to infinity, and we're concave down on the interval where x is an element of negative 1 over square root 3 to 1 over square root 3. Okay, great. Cool. I have the intervals where I'm increasing and decreasing. I have the intervals where I'm concave up, concave down. I have my minimums and my maximums. I have my points of inflection. I can draw a pretty darn good graph at this point. So we're going to lay down coordinate plane, 0, 1. 1, negative 1, negative 1, negative 1. And we know we are concave up for this part, and concave up over here, and concave down in between. And we know that from the points of inflection that point of inflection is below the x-axis. So maybe there and there, and we would of course label those points with their ordered pairs. Also, and I don't know about you guys, but that looks like a pretty accurate graph just for analyzing the function using calculus. This is a cool, fun building puzzle that we're going to be doing with first and second derivatives, analyzing the rates of change and how we can use those rates of change to draw this cool graph for really any function that I can throw at you. And that, ladies and gentlemen, is where I stop. I bid you a fond farewell.